So are you able to see my screen and hear the audio? So are you able to hear the audio and see the screen? Okay, okay. Okay. Okay, so good evening everyone. I'm Calvin Joseph and today I'll conduct your week 5 problem solving and doubt clearing session for this NPTEL course Digital Circuits taught by Dr. Sanjanu Chattopadhyay of IIT Kharagpur. Okay, so we have been doing this digital circuits course where this is your outline. And today is the week 5 where we'll be talking a little bit of arithmetic circuits, some amount of code converters, but we'll also be discussing about multiplexers, decoder, and other things. Okay. So in arithmetic circuits, we have some basic operations, that is equality, or is it greater than, less than, that operation is there. Then certain code converters, some very one which is very popular is the binary to gray code and vice versa. All right. Then we'll discuss about decoder, encoder, everything. Okay, so let's get started. Okay. So this is week 5. So I'd like the session to be interactive. I'd like you guys to either, unmute and tell, or you could also send a message in the chat. Okay, so I want you guys to tell which logic gate is best for equality comparison. If you want to do equality comparison of 2 bits, which logic gate should be used? Can anyone tell?
XOR.
XOR. Okay. Why do you say XOR gate? You're close to it, but can you elaborate a little bit more?
I think when inputs are different, XOR gives us 1 and they are equal, it gives 0.
Yes, yes. Okay, okay. Yeah. So this is your symbol of your XOR gate, right? So you have A, B, and Y, right? So you have 0, 0, 0, 1, 1, 0, 1, 1. So 0, 0 XOR will give you 0. If it is 0, 1, that is they are not equal, it will give you 1. 1, 0, if they are not equal, it gives you 1. And if it is inputs is 1, 1, that is both the bits are the same, equal, it gives you the output 0. So this is for a XOR, but if you want it in terms of, active high, you actually want it to give y equal to 1, then you have to use an XNOR gate. You have to use an XNOR gate. XNOR gate is what? It's opposite. If you have 0 and 0, that is both are equal, it will give output 1. If you have 0 and 1, they are not equal, it will give output 0. If you have 1 and 0, they are not equal, it will give output 0. And if you have 1 and 1, they both are equal, it will give output 1. Okay, so XNOR gate is useful for equality detection. Okay, that is the XNOR gate. So now, I'll ask you a question. You have, let us say, a number which is, let us say, simple. Let us keep it a number 5. Okay. How will you represent it in binary? What is the binary representation of 5? What is the binary representation of 5?
101.
Yes, correct. It is 101. Okay. So this number A has 3 bits. That is what it has: A2, A1, A0. 3 bits it has, which have the number 101. Okay. Now you have another number B, which also has 3 bits. That is, it has B2, B1, and B0. Okay. So now you want to do what you want to do. You want to check is A equal to B or not. That is your question. You are starting simple. You want to check if A is equal to B. So how will you do that?
It's not equals to a b.
Yeah, it's not equal to AB, but A has 3 bits, B has 3 bits. Then how will you do that?
Gray to binary.
Why use gray to binary?
Because then only we can conclude a equals to b or not.
No, 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 no. No, that's not the reason. See, your A has, so your number A, whatever is your number A, it has a bit A2, bit A1, bit A0. Okay. So let me keep some A2, A1, A0. Your number B has how many bits? It has 3 bits again. So B2, B1, B0. So now if A should be equal to B, what should be the same? B2 should be equal to A2, B1 should be equal to A1, and B0 should be equal to A0. Do you think that is correct or not?
No,
Why not?
Yes.
only b2 equals to a2 only equal.
No, no, no. How? See, let us say, what do you have? You have, let us say this is your number A, this is number B. It is 101. Okay. So that means it has a value of 5. Now if B should have a value of 5, this should also be 1. Let us take some color. This should be 1, this should be 0, this should be 1. But B could also have different combinations. B could also be, 1, 1, 0. B could also be 1, 0, 0. B could be all 1, 1, 1. Right? So if we want to check that it is equal, that means this should be the same, this should also be the same, and this should also be the same. Right? Or any doubts in this part?
No, no. Clarify.
Hmm? So if that is the case, that is if A has 3 bits, that is A2, A1, A0, and B has 3 bits, that is B2, B1, B0, then what you should do? You should do the XNOR of what? A2 and B2. You should do the XNOR of A1 and B1. You should, sorry, you should also do the XNOR of A0 and B0. Okay. Once you do all these XNORs, you must pass it through an AND gate. Okay, AND gate. Okay, and then you get your output Y. All right. That is, you have to first check what you have to do. You have to check if A2 is equal to B2. Very good. Then you have to check is A1 equal to B1. Okay, very good. Then if your A0 is equal to B0, then only your Y will give you 1. If any of the bits are different, then it will not give you 1. Okay. So this is the property of, what your equality detector. Okay. So to give you an idea, uh, let us say you take some bits. Okay, let's take this bit is 110. Hmm? Let us take this is 1 1 and 1. They're almost equal, but they are not exactly equal. So let us see, let us walk through. So what you have A2 is here is 1, B2 over here is 1, right? 1, 1. X nor of this will be what? X nor of this 1, 1 will be what? X nor of 1 and 1 would be 1. Okay. Now let us go to A1 and B1. A1 is what? A1 is 1. B1 also is 1. Very good. Both are equal. X nor is equality detector. So it will also give 1. Then you go over here. Let us use this color. 0 and 1. So this A0 is 0. B0 is 1. Now when you do X nor of that, then it's a problem. Then this becomes 0. So then what happens? What will happen? And of 1 and 1 and 0 gives your output 0. That means they are not equal. Okay, so this is an equality detector circuit. Any queries? You can ask me because this is a doubt clearing session only. Objective is to clear your doubts. You let me know. Okay, if you have no queries, I'll proceed further.
No, sir.
Okay, so don't be afraid of these digital circuits, everything. Because the reason, why you do engineering or why you study maths as engineers, everything is you have to gain what is known as that ability to reason, ability to, think, ponder, and, you should be able to say that if I do this, kya hoga? If I do this, what will happen? Right? That is the, your objective of you doing engineering. See, I don't know, some of you are faculty members, some of you are BTech students, some of you may be master students, some of you might be, trained professionals, everything. But, the reason we do all this studying is not that, we should have the knowledge or we should, say that X NOR gate truth table, I should know by heart. That is not the overall reason. One of the reasons which you study many things, you get exposed to many different subjects is you slowly get the ability to combine merge different things. You learn how to take this concept, apply in this concept, take that concept, apply in this concept, so that when you start working or when you start teaching or when you start doing your projects, you can learn, you can think of something new and you can try to implement. Okay, that is the thing. So actually we are engineers. Okay, you're not like uh, some mechanic, or you're not just some laborer. Okay, it's someone who just does the same work, takes one brick from here, puts it over here, takes some cement from here, puts it over there. That's not your work. Your work is you try to understand some concept. You need to know, remember some things, but further to to become much better, to understand faster and to do, you should also have some concept, some reasoning, some intuition, so that you can enjoy what you do. Okay, so that's why this is an equality detector circuit. I just wanted to stress it out with an example about how you do equality detection. Okay, so now once you have done equality detector, that is, if A is equal to B, then what we have to do, let us try something. Let us go for doing what happens if you want to find if A is greater than B. Okay, so let's continue with this example. That is, you have bit A2, bit A1, bit A0 for A. And for B, what do you have? You have B2, B1, and B0. Okay, you have 3 bits each for the numbers. Okay, if you want to do they are equal, you can get it like this. You can get it through this circuit. But now you want to do is A greater than B. Okay, so now let's, these are like what you say, there are 3 bits each. So let us say for some 3-bit number, that is x2, x1, x0. Okay, so this is your MSB, most significant bit. It has the most weightage. Okay, this is your LSB. It is your least significant bit. So it has the least number of weightage. Okay. So now, let us say, 1 minute. So let us say the bits are x2, x1, x0, and what is the magnitude? Okay. So we have, what do we have? You have 0, 0, 0. If you have 0, 0, 0, means the magnitude is what? 0. If you have 0, 0, 1, the magnitude is 1. If you have 0, 1, 0, the magnitude is 2. 0, 1, 1, the magnitude is 3. Okay. 1, 0, 0, the magnitude is 4. 1, 0, 1, the magnitude is 5. 1, 1, 0, the magnitude is 6. And 1, 1, 1, the magnitude is 7. Okay. So now you have these set of numbers. Okay, x2, x1, x0, the bits. So you focus on the bits. You're focusing on the bits, right? And you have got the magnitude 0 to 7. Okay. So just I like to just go back to what I said. I don't mean to say that, laborers or other people that they are lower in society, nothing. It's just that for their work, they need more physical energy. For our work as engineers, we need to develop our mental capacity. Okay, so that's what I just wanted to encourage you to do that. Okay. Okay. So now, so these are your 3 bits. Okay. So let us start. If you want to say that something is more heavier or something is more bigger or more stronger or has more value, like we say now, that in gate for electrical engineering, that this subject has more weightage. Okay. And then for electronics, I don't know what subject has more weightage in gate. Different things. So what a student will do is the most important subject he will, which has more weightage in the recent years, he will take that subject and he will learn that well, because the student knows that if I focus on that subject, it has more weightage, my chance of getting a higher score is more. Okay. So in the similar thinking, in that similar mindset, let us go. We want to say that A is greater than B or not. So let us focus on the MSB. So we will focus on the MSB. Okay. So your MSB can be what? A2 can be 1 and B2 can be 1. If both are same, you cannot differentiate. Okay, you cannot differentiate whether anything is greater or smaller. But let us consider a case where A2 is 1 and B2 is 0. Okay, A2, that is the most significant bit, is 1, and B2, the MSB of B, is 0. Now you look at the table. You look at this table. Okay, tell me, if the number is 1, if MSB is 1, and another number has MSB 0, which number is bigger? What do you think? Which number is bigger? Okay, tell me. That is, okay, I think you have not understood it or I'm talking too fast. Let us go slowly. I have, I took that A2 bit is 1 and B2 bit is 0. Okay, so that means what could be the possible combinations? I could say I could have this. So for eight, for the number A, it could be these combinations. Okay, for the number A, it could be these combinations. But for the number B, for the number uh, B, B, it could be these combinations. Okay, so if you just take these combinations, is A greater than B or A less than B? Which is the case? Is A greater than B or not?
A is greater than B.
I'm not able to hear. Is someone saying something or something?
A
A is
is greater
greater
than
than
B.
B.
I am not able to hear. Let me, okay, just hold on. I'll get my
A is
earphones.
greater than B.
Just hold on. Okay. Are you guys able to hear me? And can someone unmute and tell something?
Yeah,
Yes, sir.
Yes. Okay. Now I can hear. Okay. Okay. I don't know what's the issue with my laptop. Okay. So let's go back to our discussion. So for A, we have 4 lower combinations, and for B, we have the 4 top combinations. Okay. So which is greater? Is A greater than B or not?
A
If the
is
first,
greater than B.
yes, very good. Okay. So A is greater than B. So let us say A is greater than B. Now, what if, so if my A2 is greater than B2, then I will say that A is greater than B. I don't need to look at A1, A0, B1, B0. I don't need to look at it. I just need to focus that is A2 greater than B2. So this you keep in mind. Let us try so what you need to do is, for such a case, you need to design a circuit which will, okay, let's come to designing that circuit bit later, maybe to complicate it further. Let us go to that circuit later. So that is the case. So that is, let us consider if A2 and B2, suppose A2 and B2 is there, you have 0, 0, 0, 1, 1, 0, 1, 1. Okay. How do you say A is greater than B? How do you say A is greater than B when you're doing the comparison of the first MSB bit, okay, of the MSB bit? Okay. If A2 and B2 both are 0, 0, you cannot make a assumption. You cannot make a solution. So in that time, you can say that they are equal. Okay, let us say they are equal. If 0 is less than, if A2 is 0 and B2 is 1, then it is false, right? That is, it is less than, it is not greater than. If it is 1 and 0, that means it is more or it is greater. Okay. And if 1, 1, that means it is equal. At least in that sense, it is equal. Okay. So this is for A2 and B2. So what I want you to observe is that if A2 bit is 1, okay, okay. So if A2 bit is greater than B2 bit, then then it is greater. Okay, it is greater. We don't need to worry about the other things. And if A2 bit is less than the B2 bit, then it is less. So then we can stop our comparison. We don't need to care. But if A2 and B2 both are same, both are equal, then what do we have to do? Then we have to go for A1 and B1. Then we have to check A1 and B1. Okay. Yeah. So that is done. So now, if A2 is 1 and B2 is 0, that means it is greater. You don't need to compare other bits. If, let us say, if A2 is 0, B2 is 1, that means it is less. So still again, you don't need to check the other bits. You know that A is not greater than B. Okay. But if there is a case when A2 is 1 and B2 is 1, then you have to further investigate. You have to go for the lower bits. And if there is a case where A2 is 0 and B2 is 0, that is, they are equal. Those bits are equal. Then you have to go and check the next set of bits. Okay. So assume that they were equal. That is, A2 was 1 and B2 was 1, or A2 was 0 and B2 is 0. If that is the case, then what do? We will go for A1 and B1. And let us go for a easy case. Okay, let us not try to complicate things. Let us go for a case where A2 is 1 and B2 is 1. So what are the combinations? We have these 4 combinations only. Okay. Now let's go for a case when A1 is 0 and B1 is 1. Okay, so which are those possible cases? So let me okay, that is A1 is 0 and B1 is 1. So what are those cases? Of this. It is what cases? So what is for this? These are the cases for A1 0 and for B1 1. These are the cases. So again, what you will notice that if A1 is less than B1, that means it becomes what? It falls into this category, that is, it is lesser. Okay. So if your first most significant bit both are equal, then you will go to the next set of bits. And there you will do the comparison, whether it is greater, less than, and so on. And from that, you will know whether the number is greater or it is less or it is equal. Okay. Any doubts still here? Any doubt, any query, you let me know. Because why should your doubt or query linger? If you have a doubt, you let me know, or else we can proceed further.
No doubts.
Okay, okay, fine. Okay, so this is the case. So if this is the case, we don't need to worry. We know that A is not greater than B. But when do we have to worry? We have to worry when a case when both are equal. A1, B1 is 1, 1, or A1, B1 both are 0, 0. So let us go with A1, B1 are 1, 1. So we have narrowed down to this case and this case, right? Now again we'll compare if this is 1 and if this is 0, then directly we can say, then what will happen that this is 1, this is 0, it is greater. So that means your A is greater than B. Okay. If not, if this is also 1, then we know, right, that A is equal to B. But if this was 0, then we know that A is not equal to B. Okay, like that is the procedure. So let me go back from the start. Okay, let us go back from the start. From the start, our main, as engineers, we are looking for checking. Is A greater than B? We want to know is A greater than B. So we go for the most significant part. That is the most significant bits. We compare A2 and B2. Okay. When we compare A2 and B2, if A2 is greater than B2, then we know that A is greater than B. But in case if A2 and B2 both are equal, okay, that means in terms of the most significant bits, both have the same weightage, same magnitude, then we go to the next set of bits. Okay, when we go to the next set of bits, again we do that comparison. Is A greater than B or not for that set of bits? And once we do that comparison, if A is greater than B, then we say that A is greater than B. But if A is less than B, we say that A is less than B. But if we see that the bits are equal, then we have to go to the next set of bits. Okay. So that is the iterative process in which we check the bits. Okay. We check the bits from the most significant bit to the less significant bit. Okay. Now I have one question for you guys to solve. Okay. Let us say we have the bit A2 and the bit B2. Okay, it can have 4 combinations: 0, 0, 0, 1, 1, 0, 1, 1. So that means we want to, and our output, what we are looking for 2 outputs. Okay, 2 outputs I want. One is A2 greater than B2? That is one output I want. Another output I want is A2 equal to B2? Okay, this is the truth table I want. So if I'm looking, let's go from the first. if I'm looking for A2 greater than B2, for 0, 0, what is it? True or
Zero,
false?
zero, 1,
0.
0.
Yes, right? Only when A2 is greater than B2, I will have 1. Now, if A2 is equal to B2, that means what I'll have? I'll have 1, 0,
0,
0,
0,
1.
1.
Okay. Now, for this, we already just now did. We have to just use an XNOR gate. An XNOR gate will implement this. Okay. But I want you guys to tell me which gate I must use to implement A2 is greater than B2. Which gate should I use? Which gate or which combination or what logic should I use to find A2 is greater than B2?
A2 into B2 bar.
Very good, very good. So you have to do A2 into B2 bar. Exactly. Okay, very good. So this is the things for checking whether A2 is greater than B2 in that bit level. Okay, for those set of bits. So now you'll also similarly have to do A1 B1 bar to check if A1 is greater than B1. Also, you'll have to do A1 equal to B1. You'll have to use another XNOR gate for that, right? And if you want to do A0 greater than B0, for that you'll have A0 and B0 bar. And if you want to do A0 equal to B0, again you'll have an XNOR gate. Okay, XNOR gate. So now, what is my output? My output is A is greater than B. A is greater than B. A greater than B, we have to find what truth table, not what truth table, what logic gates, what combination we need. Okay. First is A2 greater than B2? If A2 is greater than B2, that means what? Our Y is 1. Okay, our Y is 1. If this is not happening, we will look at is A2 equal to B2? If A2 is equal to B2 and A1 is greater than B1, A1 is greater than B1, then also our Y is 1. Okay. And another combination is if A2 is equal to B2 and A1 is equal to B1 and A0 is greater than B0, then our Y is 1. Okay. So we have 3 combinations. Okay. So our output Y will then be, this combination A2 greater than B2 is what? A2 greater than B2 is A2 and B2 bar. That plus, that is OR function, we are ORing it. Plus, if A2 is equal to B2 is what? A2 XNOR of B2. I think that this is the symbol for XNOR. If I'm wrong, you correct me. And A1 and B1 bar. Okay. Then you again OR it with this combination, that is A2 XNOR of B2 and A1 XNOR of B1. Sorry. And A0 into B0 bar. Okay, so this is your logic circuit which you need to check if A is greater than B. Okay, this is a bit of a long explanation. If you have any doubts, any queries, you let me know. Or if you want me to repeat it once more also, I can repeat it. Because this is interesting.
Once the equation, can you explain?
Okay, this equation, huh?
Yeah.
Okay. So this equation is representing this. Okay, it is representing this. So this is like your intuition. That is what we studied. What we studied is if A2 is greater than B2, then my output Y is 1. Okay, this is my output Y is 1. If so, that means I need an output 1. Okay, that means my whatever this Y is there, it should get a 1 if A2 is greater than B2. Okay, it should get a 1. So
I understood. I understood.
yeah. Yes. So basically, it's an OR gate. So let me just draw the circuit. Let me draw the circuit. This is OR gate. Okay, OR gate. A2 is greater than B2. For this case, then you use an AND gate over here, where the input is what? Either A1 is greater than B1, or and at the same time, A2 should be equal to B2. Okay. And then for a final case, you have this AND gate, which has three inputs, which has what? A2 is equal to B2 and A1 is equal to B1. Just a minute, sorry. And A0 is greater than B0, then this is your logic. Okay. So basically, you're understanding your problem, what is required of you, and then you're making this. Okay. So this is just a simple, it takes some time to understand, but once you understand it is good, it is easy for you to realize, for you to visualize and all that. And then hopefully as time goes, when you do some interesting projects and or you have some assignments or you're in your workplace or as a teacher or professor, you can use these things, to let students understand more. So this is like, actually many times we study engineering as just, to mug up something, that is to by heart. We have to by heart this answer, by heart this formula, and then in the exam we will just write down that and then we will forget that. Okay, if you study in that way, okay, you may get very good marks also, is possible. But you have not, got that, you should develop that understanding, that method of thinking, that method of analyzing something. Because if you develop that, it will help you further. Okay, that even though you forget many things, okay, you may forget the truth table of XNOR also, you might forget, but you'll sort of have the logic. Okay, that I should look for this, then I should look for this, then I should look for this. Okay, and then you'll slowly, what will happen is you'll start developing a pattern. You'll be able to detect that if this is happening, then I should look in this method. If this is happening, I should look in this method. Okay, that kind of, that ability to think in terms of design, that you should slowly inculcate. Okay, that is like really not stressed upon in engineering as much as it should be, but it would be good if you can develop that method. You can, stand out from your competition. Okay, because if your target is just, to just study something, by heart it and write in the exam, then, even AI can do that, right? But what if, you are able to think better, able to understand better, able to analyze better? Okay, that is will give you, a sort of edge versus your competition. Okay, so this is for equality detection. Let us go for something known as code converters. Code converters. Okay. Uh, we'll just focus on the gray code and we'll just go for a three-bit case. Let us not complicate it. This is sorry. This is in B2, B1, B0. Okay. G2, G1, G0. So this is what 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1 1 0 1 1 1. Okay, this is a normal binary representation. Okay, you might get bored of writing it, but I'll recommend when you study, you write it. It should become very crystal clear. And don't write 0 0 then 0 1 0 like that. It's not the way. When you're writing this binary representation, go in the sequential manner. Okay, it's important. So this is what this is 0 1 2 3 4 5 6 7. Now when I'm going from 0 to 1, okay, I'm going from 0 to 1. What is happening? One bit is changing. It is okay. But now I am going from 1 to 2. In that case, what is happening? 0 is changing to 1, 1 is changing to 0. 2 bits are changing. Now, if I am going from 2 to 3, what is happening? Only 0 is changing to 1. But then, now what is happening? I am going from 3 to 4. When I'm doing that, what is happening? 0 is changing to 1, 1 is changing to 0, 1 is also changing to 0 again. 3 bits are changing at a time. Okay. Then if I'm going from 4 to 5, only 1 bit is changing. Okay, only 1 bit is changing. I'm very happy. Now, if I'm going from 5 to 6, what is happening? 0 is changing to 1 and 1 is changing to 0. 2 bits are changing. And if you're going from 6 to 7, then only 1 bit is changing. Okay. So what I want you guys to look into this is that there is a case when 2 bits are changing at a time and 3 bits are changing at a time. So when the number of bits are changing so much, there could be a possibility of error. There could be a possibility of error. So that's why people came up with something known as the gray code. Gray code is that it will represent numbers in such a way that only 1 bit changes at a time. Okay. So how do you represent gray code? This is what 0 0 0 is fine. 0 0 1 also is fine. Okay. But then what happens is you go from 0. This you have to make it 1, but this also will remain 1. Because at a time you can only allow 1 bit to change. Okay. Then what do? Then you make this 0 1 and then
0.
this is 0. Okay. Then what is done is you have to make this 1 1 and 0. Okay. 1 bit is changing. Uh, then what is happening after that? Then this changes, and this changes. Okay. Then what is the pattern after that? Yeah. Then this is there. Then this will change, and then this will change. And then finally, this will be 1, this will be 0, this will be 0. Okay. So I've used some way and I've got it. Let's see. You look at it from here. Okay, let us see from here. What is happening is you're dividing it by half. Okay, let's divide it by half. So in the top, all these are 0 and all these are 1. Okay, fine. Now you know that 1 bit only has to change at a time, and accordingly we have written this sequence. Okay. So if you will observe this number, they are the same. Okay. You observe this and this. They are also the same. If you will observe this and this, it is also the same, right? If you observe this and this, it is also the same. So that's why there is a sort of pattern, and it is also known as reflected code or something. I'm not sure, I've studied lot some time back, but it has some sort of pattern. Okay, so that could be a way for you also, to check whether you're getting the right answer or not. So this is from binary to gray code.
Sir, apart of this,
Now,
we can do like this also, na?
Like what?
B2 equals to G2 is same.
Yes, is correct.
Then we have to know G1. B when we XOR B2 XOR B1, we got G1.
Okay.
When we
Okay.
B1 XOR B0, we got G0 now.
Actually, I think you're close by. There is some circuit. Let me just see what. Okay. Yeah. Acha. Yeah, the circuit, how is the circuit, which sir also has shown in the lecture is B2 will directly go for G2. Okay. But B1, you will compare it with XOR and that will generate your G1. And B0 also you will compare it with your XOR and that will generate your G2. Okay. Hmm? This is the way you get from binary to gray code. This is your circuit which is used for converting. So let us take an example. Okay. Let me give you some set of numbers for you to get believe in everything. Let us say this is 1, this is 0, and this is 1. What will be G2 in this case?
1.
Yes, G2 is 1. What will G1 be?
1.
1. Okay. What will G0 be? Oh, sorry, this will be G0. What will G0 be?
1.
Yeah. Okay. So that means we are looking at which combination? This combination, right? B2 is 1, B0 is 0, B1 is 0, and B0 is 1. And then what you get at the output, all are 1, 1, 1. Okay. So this is like a gray code converter. This is like a gray code converter. Okay. Right. So now, if you want to go from, let me give another little bit difficult one since you all are learning. Let us take 1, 0, 1, 0, 0, 1, 1, 0, 1. This is your binary. You have to convert to gray code. How will you do?
1, 1, 1, 1, 0,
1, 1, then
1,
1, then
1,
1,
0,
0,
1,
1,
0,
0,
1, 1.
yes. Okay. This bit simple. From binary, you're just going to gray. You directly pass this. MSB, you just directly pass. Next onward, you get from the XOR combination. XOR combination of the two bits. Okay. So this is for binary to gray. There is also something for gray to binary. Let me draw it on a different page. Gray to binary, let me see what's the circuit. You have G2 that connect to B2, or this you have XOR. P2 gets fed back here, and you take G1 here, and you get B1, and then you do another XOR where you get B0. B1 gets fed back, and you have G0. Okay. So let's take numbers. Okay, let us use numbers, practical examples. Let us take this is 0, this is 0, and this is 1. Okay, 0, 0, 1. So what happens? B2 becomes what? It becomes 0 directly. Now the 0 and XOR 0, what does 0 XOR 0 become?
0, 0, same
0. And then 0 XOR 1,
1.
1. Okay, so now it's the same. Did we make any mistake? Let's go and check in the table. This is also same, right? If you will observe this one, this is G2 is what? 0, 0, 1, and this also is 0, 0, 1. So in this case, it does not get modified, right? It doesn't get modified. Okay, so this is just something which let's go further. Let's try something harder because yeah, you guys are smart. You guys are capable of much more. So let's try 1 1 0 1 0 0 1 1 0. Okay. This is in gray code. Now you have to convert it to binary, right? Binary. So first one will be just 1 directly. Okay. Then what you will do, you will
1,
check. So what, 1 minute. This directly comes here. Okay. And then you will check XOR of this and this. XOR of this and this. 1 XOR 1 is what? What is 1 XOR 1?
0.
Yeah, correct. It is 0. Okay. Now you have to check XOR of this and this now. Okay. So what is the XOR of 0 and 0?
Same 0.
0. Okay. Now again you have to check XOR of 0 XOR 1. What is that?
1.
1. Okay. So similarly 1 XOR 0 becomes 1. Again 1 XOR 0 becomes 1. 1 XOR 1 becomes 0. 0 XOR 1 becomes 1. 1 XOR 0 becomes 1. Okay. So this is how you convert gray code to binary. Okay. This is just a example. All right. So any queries still here? Any doubts? Anything to ask?
No.
Okay, fine. So let's just take a break of 2 minutes. Okay, we'll just take a break of 2 minutes and then we'll restart. Hmm? Okay, 2 minutes and then I'll just check your doubt after 2 minutes. Huh? Okay. Okay, so Oppo, you're having doubt in this binary to gray code or gray code to binary? Okay. Uh, let let me just give a small recap about gray code converters. Code converters that you have certain representation of code. It is in some format. You're converting it to another representation for a certain use, for certain safety, certain precaution, or certain application. That is a code converter. Okay. So binary, if you notice that the bits changes a lot from one bit to the next, from one number to the next number in the sequence, there can be 1 bit change, 2 bit change, or even 3 bits of change. Okay, so that's why people came up with what is known as a gray code, where only 1 bit changes at a time. Okay, so that's the gray code, which is over here. This is your gray code. Now you have a circuit to convert binary to gray code. All right. See, we as human beings, we do something, right? We can think, we can analyze, we can remember and do. But when you're making this machine or the circuit, do you have certain function? Okay, so you have this set of circuit. You use a couple of XOR gates. MSB goes directly as the MSB for your gray code. But the remaining bits you do XOR individually and you get the gray code of that. Okay. So that's how binary to gray code you can do. But when you go from gray code to binary, same as the MSB will directly go as your MSB, but then there will be a feedback. Okay, that is G1 will be XORed with B2. G0 has to be XORed with B1. Okay, that's how you get it. So from going from gray code to binary, it is a little bit challenging, little bit complicated. Okay. All right. So I hope that has solved your query. So now let's go to something known as an encoder. Okay, not encoder, sorry, decoder. Decoder is what? Let's go for a 3-bit or 2-bit. Let's go for 2-bit only, simple. You have A1, A0. Okay. And it will have 4 outputs. O0, O1, O2, O3. Okay. So what it says, if A1, A0, what does the magnitude mean? 0, 0 means the magnitude is 0. And then you have 0, 1 means the magnitude is 1. 1, 0 means the magnitude is 2. And 1, 1 means the magnitude is 3. Okay, you have 4 outputs. So you have O3, O2, O1, O0. So when the magnitude is 0, only this will be 1. All the rest will be 0, 0, 0. When the magnitude is 1, only this will be 1. All the rest will be zeros. Sorry. All the rest will be 0, 0, 0. When the magnitude is 2, this will be 1. All the rest will be 0, 0, 0. When the magnitude is 3, this will be 1. All the rest will be 0, 0, 0. So basically, your binary number, you're decoding it. And you decode it at some particular function. Okay, O0, O1, O2, O3. It will be high, only one at a time. Okay, this is known as your decoder. Hmm. So now there's another interesting circuit which is known as a multiplexer. Okay, multiplexer. So multiplexer is something. Okay, let's just look into what is a multiplexer. Let's go for a two input multiplexer. 2:1 multiplexer, mux. Okay, you have input A0, input A1, and this is, you have a single output. Okay, output. And then you have what is S. This is known as your select line. Okay, this is known as your select line. So what does it do? When S is 0, what is your output? Okay, seems very confusing. Let us take simple. Let us say this is Y. When S, that is your select line, is 0, your Y is equal to A0. When your S is 1, select line is 1, your output is equal to A1. Basically, it is like connecting. It is like connecting. If S is 0, what happens? This is gets connected. This one S is 0. And if S is equal to 1, A1 gets connected. Okay, this is this is what a multiplexer does. Okay. We also like we also like to, to do multitasking. Okay, we want to do this. We want to attend class. We also want to use our phone, and we also want to listen to music, and we also want to read some news, or we also want to answer a text message. We also like doing multitasking. But one thing you must remember is, usually most people, like at a time, you cannot do multiple things well. Okay, you either do something and then you go to the next thing, and then you go to the next thing. Okay, your attention at a time, it is quite difficult to do multiple things well. Okay, we have a concept like we can be studying something and our mind can be somewhere else. That is also possible. That we like to do that. But if you want to study well, if you want to do something well, it is best if you focus on one thing at a time. Okay, so similarly, in a multiplexer is something that it has getting A0, it is getting A1. Okay, but at a time, it should pass only one of the signals to the output. So if S is the select line, select line says I will select to do this or I will select to do that. Okay, select line, if select line is 0, means at the output Y, it will get A0. If the select line is 1, at the output Y, it will get A1. Okay, that is the concept of a multiplex. Now, you could have a bigger multiplexer as well. Okay, so there are certain people who are, very important. They have many, many things to do. They have a task called A0 is also coming, A1 also comes, A2 also comes, A3 also comes. It has to go to the output Y. Okay, now, if I just use S, I cannot decide, whether I want to need A0 or A1 or A2 or A3. I cannot do that. So in that case, you have two select lines. You have a select line S2 and you have a select line S1 as well. Okay. So what happens is, if S2 is 0 and S1 is 0, then at your output Y, you will get A0. If S2 is 0 and S1 is 1, at output Y, you will get A1. If S2 is 1, or S1 is 0, at output Y, you will get A2. At S2 is 1, S1 is 1, at your output, you will get A3. Okay. 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 Yes. Okay. With enable input also we will do. Okay. So this is your 4:1 multiplexer. Okay. Now, we have to have enable input as well. Okay. So we also can add something known as a enable line. Okay. This is your enable. So what is enable means? Enable says that if it is 1, then your output will work. Okay. So over here, you must understand enable also is there. And this is 1, 1, 1, 1. Then your output Y is comes like this. Okay. Now, if your enable is 0, right? Enable is 0. That means okay, 1 minute. If your enable is 0, whatever is the case of S2 or S1, your output Y will not be A0, A1, A2, A3. I'll have to check. If your enable is 0, what is your output Y? To be output Y in that case, it I don't know. There may be some definition. Either it may drive it to 0, or it may be high impedance, or it may be undefined. So enable is like sort of, saying either you pass the inputs or you don't pass. Something like that. Okay, that's your enable. Okay. Then okay, let's see the use of enable. Okay, let's see one practical use of enable, which probably Sir also has shown, but we'll just see. This is your 4:1 multiplexer. Okay. It has A0, A1, A2, A3. Okay. For this, you select an S1, S2, S1. Okay. And you use your enable. Similarly, you can have another 4:1 multiplexer. This can give you a Y1. Okay. Y1. Which will get your A4, A5, A6, A7. And this is another 4:1 multiplexer. Here you give S2, S1. And instead of enable, here you will give enable, and at the top you will give enable bar. Okay, so you get Y1 and you get Y2. And Y1 and Y2, what you will do, you will pass it through a 2:1 mux. Okay, and that will give you your output Y. Okay, and for that also, if I am not wrong, which one should we take? It would be enable one, I think. Yeah, it would be enable. No, it should be enable, right? That is true. So you have enable S2, S1, and Y. S1, Y1, Y2, and Y. This is 0, this is 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay. If enable is 0, okay, enable is 0, that means Y1 will either get, this will be A0, A1, A2, A3. Yeah, under this combination. And Y2 will be, undefined sort of, it will be undefined. Or I actually don't know whether it will be high impedance or something, but it will not be active. It is not enabled, okay? It is not enabled. Now, in this case, what happens? This is not enabled, this is not enabled, and this will be A4, A5, A6, and A7. Okay. And then in your output Y, you will either get A0, A1, A2, A3, or A4, A5, A6, and A7. Okay, that is what your enable will function as. Okay. Yeah. So I hope this has enabled you to understand multiplexer. So there was one more query about the clock. So who asked that query? So where did you come across a clock, Sumit? You can text also. Okay. Okay, very low classes. Okay, okay. Yeah. So for your digital circuit to run, you will run it with a clock, with some synchronization signal, that is your clock signal. Okay. So in that case, we represent a clock. So basically you have a high frequency. Let me use a different color. Clock is a signal. Like this is like your base signal. Okay. That means your digital circuits will run at that rate. So you'll have some clock coming like this. At this speed, you have certain clock pulses. At that rate, your digital signal will run. So your multiplexer, so let us say you have a 4:1 or some mux you have. It has some signal A0, or let me not use A0, it is confusing. Let us use D0, D1, D2, D3. Okay. You have your select line S2, S1, you have a select line enable. Okay. But you should also have a clock will be there. So at the clock edge, then only your output Y will change. Okay, even if your S2, S1 changes, only at the clock rate, whatever is the input signal will get connected to the output. So clock is like at your rate at which your digital circuit or your mux will function. That is the role of your clock. Okay, I hope that has cleared your doubt. So you're learning Verilog from which place? From where are you learning Verilog? Okay, okay. From Indranil Sengupta's course. Okay, okay. Fine, fine. All right. So, what? So let us see a function of a mux. Okay, let us just go for a simple thing of a mux. Let us try a 4:1 mux. Okay, this is our signal. Let us say this is our D0, D1, D2, and D3. And this is what? Okay, let me go with a 2:1 now, so it is simpler to explain. You have a 2:1 mux. Okay. What you get at the input here, you get a D0 or you get a D1. Okay. And this is your select line S. And this is your output Y. So what is your output Y defined as? So we know the truth table, right? You have select line S and Y. This is 0. This is going to be your D0. If this is 1, your output is D1. So your Y is actually equal to S bar into D0 plus S into D1. This is your truth. This is like a Boolean expression of 2:1 mux. Okay. This is a Boolean expression of the 2:1 mux. Now, if let us say you make D0 to be equal to 1 and D1 to be equal to 0, then what will be your output Y? What is the output Y in such a case?
One.
D0 is 1 and D1 is 0. So what is the Boolean expression for Y?
S bar.
Yes, Y is equal to S bar. Okay, so let's go for something else. Let us say with this 2:1 marks, we have very limited options. Let's go for 4:1 marks. Let us have a 4:1 marks. Okay, these are your select lines. Let us take these select lines as A and B. Okay, instead what we were representing, this is S2, this is S1. Let us cite it as A and B. What's the problem? It is just some representation, right? This is what, this is your D0, this is your D1, this is your D2, this is your D3, and this is your output Y, right? So what is your output Y? Y is what? If A bar is A0, B is 0, then your output Y is what? D0. That is why it is A bar, B bar, D0. If if A is 0 and B is 1, then it is your D1. If your A is 1 and B is 0, then it is your output D2. If your A is 1 and B is 1, then it is your output D3. So this is your output Y. Okay. This is your output Y. Now, let us say that D0, you make D0 as 1, D1 as 0, D2 as 0, and D3 is 1. Then what circuit you will get?
What, sir?
If I make D0 1 and D1 is 0, D2 is 0, D3 is 1, what will be the expression for Y?
A bar, B bar
Okay. Hmm.
plus AB.
Okay. So can anyone tell what is the logic gate for this expression?
XNOR.
Yes, exactly. This is the XNOR of A, comma B. Okay. So, very good. Any other? So, any doubts still here? Yes, good read. It is XNOR. Okay. So, sir had also taught regarding encoder and priority encoder. You could also check that when you have time. Okay. I was thinking of showing some simulations. Okay, these simulations are optional. These are not for like compulsory, or you won't be evaluated based on that. But it is something just I just felt it would encourage you to learn digital circuits, to understand digital circuits. And that's why I was thinking of checking some simulations. So I'm planning to start that. If you're not interested in that, you may leave the session. Okay, before that, if you have any doubts, you can ask me. And then if you don't have any queries, I can start with the simulation. Okay, projects for learning purposes. Um, I don't know actually, like learning purpose. You can start with certain simulations of these things. And after that, uh, some very simple projects which people can do is like you have the 7 segment display. That is one thing. And you can also do counters in digital circuits. And what else is you could do? You could generate PWM waveforms, pulse width modulation waveforms, using counters and comparisons and other stuff. Okay. Then Then you have microprocessor, microcontroller, all that. So those also you can explore. So Sumit, like you're basically you're what? You're a BTech student, you're a MTech student, or you're a working professional. Like what? If you're from BTech, which department? Electrical, electronics, communication, which one? Okay, you're currently working on RF systems. Okay, if you're working on RF, then basically your work is related to analog, right? Mostly analog. Uh, there, digital, how can it be used? Not very sure. You could focus on things like ADC, DAC. That could be something you can focus on. Analog to digital converters, digital to analog converters. Okay, digital signal processing. Digital signal processing, then you can try certain filters, IAR, FIR filter, and design of the filter, and check the response of the filter. Mm, and yes, you can do in digital. Mm, you could also try generating FFT also, fast Fourier transform of your signal and all that. FFT and uh, maybe checking RMS value and those things. That is something you can do. But if you're working on RF, that is basically what? Are you working on chips? Are you working on IC chips and all? Or are you doing simulations, doing cadence simulations or something? Or are you testing some integrated RF circuits?
For
Hmm.
PD, sir.
For?
PD.
Okay.
Physical design.
Oh, physical design. Oh, those things I don't know much actually. I don't know much about physical design, everything. Uh, because I have not worked on, this integrated circuits actually. Integrated circuits, basically you need lots of electronics knowledge, and I am from electrical background. My electronics is quite weak. Okay. Uh, and to what I've heard, what I've seen in IT, IT Kharagpur, from the few people I've met with, basically they have to, think of what is the application of their circuit. Based on that, they will, make a schematic, and then they will size the transistors and they will run simulations. After they do that extensive simulation, they start from an ideal block. Then they will slowly, make it more practical, and they will fine tune it. After they do that, then they will run corner simulations and certain things. Then they go for, I don't know like, whether I'm going the exact flow. These are certain things they do. Then they go for layout, then post layout simulation, then they go for tape out, and then they get the chip. Then they take the PCB, design a PCB for the chip, and then they test it. That is how I've seen, like to very few what I've seen. So that's it. Okay, so Sumit is shifting from analog RF systems to software defined radios. Okay, okay. So uses FPGA, CPLD, and ASIC. Acha. So then you can do many things with FPGA, and you can probably get some. For FPGA, I think you are going through that Indranil Sen Gupta sir's course, so that is good. you can try those things, write a Verilog code, simulate that simulate it. And but basically, like, what equipment do you have? Do you have any oscilloscope? Do you have any FPGA kits or something which you can work on?
Sir, in which domain you have interest?
Uh, my domain is actually I'm working a bit in power electronics actually. So for that, it is basically already, those big transistors are there and PCB I have to design and those things. So it is not exactly digital electronics. I just need digital electronics for, using the FPGA or microcontroller for certain aspect, but this hardcore digital electronics is not what I'm doing. Yeah. Hmm. So Sumit, you use FPGA, CPLD, and okay, so software defined radios uses FPGA, CPLD, and ASIC. Okay. Uh, so ASIC is something which is very specific. Yes, sir. So you have signal generators and spectrum analyzer you have. So you're soon gonna buy an FPGA kit. Okay, that's very good. Okay. Uh, mm, but how will you? So do you have an oscilloscope? Do you have something to view your signals? Okay, okay. Then I think you can do many things. Yeah. Only you like it. I'd recommend you have to do software defined radios, right? So you can go to a software defined radio, some product which for SDRs. You can see what chips they're using. Okay, what FPGA chip they're using, what ASIC chip they're using, what CPLD chip they're using. Okay, ASIC chip is like it is for some particular application. So you can understand that what application they're using. You can go to the data sheet or that reference design or something, and then you can first get
हाँ
a.
सर
Yes, yes, yes.
सर वो असाइनमेंट 3-4 का जो सॉल्यूशन है वो सर रिलीज नहीं आया है अभी तक।
अच्छा अच्छा, उसके लिए आपको मेल करना पड़ेगा। आप उनको मेल करो या जो।
इसमें सर जो असाइनमेंट स्वयं का जो है असाइनमेंट 1-2 वीक 1 वीक 2 में ही तो सॉल्यूशन आता है।
अच्छा अच्छा अच्छा,
उसमें
वीक 3।
1 और 2 का है लेकिन 3 4 5 6 का नहीं है।
अच्छा अच्छा, 5 का तो नहीं आएगा ना, 5 को अभी आपको सबमिट करना पड़ेगा, उसके बाद
5 का
आएगा।
नहीं, 3 4 का नहीं आया अभी तक।
अच्छा अच्छा, उनको एक काम करो, उनको मेल करो या कुछ तो ये रहता है ना। आपको कुछ फोरम है ना, वहाँ पे आप मेल करो। ठीक
जी
है।
मेल किए हैं तीनों, जैसे हम लोग मशीन 1 का भी लिए हुए हैं, उसका भी 1 आया है, 2 आया है और 3 4 5 नहीं आया है, 3 4 नहीं आया है।
ओहो। अच्छा, आपको मेल ही करना पड़ेगा। मैं मैं
मेल
एक्चुअली
कर दिए हैं
उनके
सर
साथ।
लेकिन अभी तक आया नहीं है।
अच्छा अच्छा, क्योंकि मैं तो सिर्फ ये पढ़ा रहा हूँ, मैं एक्चुअली ये कोर्स का मेन वो नहीं हूँ। वो उन लोग एनपीटीएल वाले लोग ही देखते हैं। एक बार वापस उनको मेल कर दो। हम्म। या आप किसी दोस्त को भी बोलो मेल करने को एक साथ, वैसे। रिप्लाई नहीं आया क्या?
So just tell me,
हम्म।
uh, if I know 80% of digital electronics and 50% of CMOS VLSI,
Okay.
then is it enough for as a fresher or not?
Pressure is not, I can't say actually, because I'm not in companies. I have not yet worked in any company, right? And I don't have that many friends. I have very few people who I have spoken a little bit with who are working in these companies, but I don't know. Yeah, yeah. Yes, yes. So I cannot exactly say. You can ask people on who have joined those companies, who have joined as freshers, what exactly are the requirements. That is best. Okay. Because since I don't know, I just cannot give you advice with that. Oh, yeah. Yeah, Sumit, yeah, Sumit, you can check for some kits. You can check for some good FPGA kits. And based on the SDR applications, what FPGAs are using, based on that, you can check the kit. Also, when you're buying an FPGA kit, you make sure that you can also program it, that it should be easily programmable. The softwares for that also should not be costly or expensive. Okay, unless you have the software and other things, it's fine. But if you're just a fresher or just someone new, okay, which doesn't have much expenses and other things, go for a simple FPGA kit and something which you can use free software and run. That is important. Yeah, that's there. Okay. Yeah, so Bijam, I cannot exactly recommend since I have not yet, started working. I'm still studying, still a student, still learning. And you can ask those people who have graduated, who have started working in companies where you want to join. So you can ask them how what was asked in the interview, what was asked in the test, what are the companies looking for, and what they actually work in their company, so that you can prepare accordingly. Huh? And you can, and maybe you start giving interviews and tests and other things, you will slowly improve. You'll slowly get to know what they exactly are looking for. Okay. So let me start with certain simulations. Let us look into it. Let us see whether it will work today. Okay. This is a D flip-flop. Okay, flip-flops are not come till now. Okay, let's start with a simple thing. Let's start with a counter. Okay, let us implement 2:1 mux first. I need a counter, no, for generating test signals. Okay. Sure. So I'll start with a counter, okay, which is 2-bit counter, and it plays a digital pulse generator. Yes, digital pulse. Let us make it 1 microsecond is fine. Simple. And number of bits 2, maximum count is 3. Okay. So this is my D0. It's a digital thing. This is my T1. This is also a digital thing. And this is a clock signal. Okay, clock. It is also digital. Okay, let me run it now. Segment, use analysis, transient, 1 micro. So let me do 10 micro. Yeah. Okay, so this is run. So what I want you to notice is this is my clock. Okay, so Sumit had asked, clock is your base frequency, your base rate at which your digital circuits are implementing. This is mainly important for your sequential circuits. Okay, so your counter is a sequential circuit which you will know, which you will soon learn. But I want you to understand this. There are counters. This is a 2-bit counter. It is bit D0 and it is bit D1. D1 is your MSB, D0 is your LSB. So how do you go? You go from 0, 0 over here. Then you have 0, 1 over here. Then you have 1, 0 over here. And then you have 1, 1 over here. Okay, this is your counter. Okay, let us see if it would make it easier for you if I put a DAC. That may give you a better idea. Number of bits to select offset voltage, it is kind of industry. This there's a digital to analog converter also. This is the number. Magnitude. Okay, let's see. Yeah. Okay. So this is the magnitude. Okay, you have the clock you have, then you have D0, D1. Then you go to your DAC. So if D0, D1 is both 0, 0, the magnitude is 1. Oh, I should make them, sorry, 4 and that will 3. Range is 3. Oh. Let me resimulate it. Okay. So clock is your base command, D0, D1 are there, and this is your magnitude. If D0, D1 both are 0, 0 in magnitude sense, in the number numeric sense, it is 0. If D0 is 1, D1 is 0, it is 1. It means 1. If D1 is 1 and D0 is 0, it means 2. And if both are 1, that means it is 3. Right? So this is like what you do, right? Normal numbers, how you say, right? You have 0, 1, 2, 3. Okay, so D0, D1 are changing accordingly. To generate this D0, D1, we used a mux. Okay, we used a mux. Now, what we have to do is, so we have used a counter to generate D0, D1. Now, let us try to make a simple 2:1 mux. Okay, our objective is we have to make a simple 2:1 mux. So we will also generate another signal. This is a digital pulse. Let us generate another pulse. We will connect a probe there. Let me now connector also. Please connector. This is my select line. Yes, select. Let me change the period. Let me make it 5 micro. Width, let me make it 2 micro. Start delay this. This you select. This also a digital thing, so I make it digital. And then you run. Yeah. So this is my select line. Okay, this is my select line. Okay, a select line has been made. Okay. Now we have to make a 2:1 mux. Okay, and if we have seen, so let me open that what I used just now. This is the logic, right? S bar into D0 plus S into D1. This is the logic for a 2:1 mux. Okay, so we will do that. Okay, we will do that. So you have to first place digital inverter. Okay. Then we take select line. In terms of connector, let me connect this. This will be my D0. This will be my D1. Okay. Now select line, I will AND it with this. S bar is ANDed with D0. Okay, like this. Similarly, select is ended with D1. Okay. Then you have to do OR of that. So place digital OR to input. This is it. The mux output. Okay, let us connect a probe also over here. Mux out, which is also digital. Now let us run it. Yeah. So this not visible. So let us see. Let us try to understand. Okay, the select line, let me change it a bit. Make it more. Let us make it 5 micro and this let us make it 4 micro, 10 micro. Okay. This magnitude I don't need now. See that. Let me run it for more time. 20 micro. Okay. I will run it. Now, if you're, let us see your clock, you have D0, D1, mux out, and select. Okay. D0, D1 are your inputs to your mux. Okay, D0, D1 are your inputs to your mux. If your select line is 1, okay, if your select line is 1, that is select line is I, your mux output will be same as your D1. That is why your mux output is same as your D1. Okay, it is same as your D1. When your select line is 0, then your mux output is same as your D0. So it is same as your D0. Mux out is same as your D0. Then when your mux out becomes 1, then it becomes same as your D1. It follows your pattern of D1. Okay. Then when it becomes equal to 0, it follows your pattern of D0. Okay, it follows the pattern of D0. That way it goes. Let me now just put an offset so that it will make more sense. Offset of 0.5. Okay. So whenever select is 1, okay, whenever select is 1, you're taking whatever is D1, you get it. Whenever select is 0, you take whatever is D0. You take whatever is D0, you take it from there. Again, when select changes, you take it from D1, and when it becomes 0, you take it from D0. Okay. Any queries in this? So here I feel that if a clock is added, if a clock is added to your mux configuration, it would make it better. Otherwise, sometimes it is being a wrong signal, like this signal over here. Sorry, this combination over here. No? Suddenly it is this, then it goes low, everything. It is not synchronized. So proper synchronization might be a clock, may improve, I don't know. I'm not sure. No. This is how it is looking. So it is fine. Yeah. Okay, so this is a demonstration of a 2:1 mux where it is made in Simetrix software, which is in the Elements version. Elements, Simetrix Simplest Elements, which is a free version. It's a free demo version which you can use for simulating, these logic gates, these digital circuits, etc. This is a very simple one, but I'll advise you start with the simple ones and then you go for advanced and complicated stuff. Okay, you learn how to probe it, how to display waveforms, how to generate test signals, everything. Then it will make your way study faster. All right. Okay, let us try something else. Mhm. We want to do binary to gray code, which we also did recently, right? So we had done a 3-bit example. So let me change the number of bits to 3. That I don't think we need right now. We make this B0 binary. B0, B1, B1. Is our B2. Let's get connected over here. Okay, let's put a probe also. B2, which is digital. Okay, so you have B0, B1, B2. Now, this is a counter that is generating it. Let us see whether it's generating fast. Correct. Yeah, select line is not needed over here. So, clock. So B0, B1, B2 is all generated. Yeah, 0, 0, 0, 0, 0, like 1, 0, 0, 0, 1, 1, like 0, 0, 0, 1, 0, 0, 1, 1. Okay, like that it is being generated. The test signals are being generated. Now, we have to pass it through a gray code converter. So gray code, what is gray code? What did we see? What is the circuit which sir has shown? This is the circuit. Okay, B2, B1, B0. B2 goes directly to G2. B1, how it is converted to G1 and all, we'll see. So this is your B2. It goes directly to G2. This is simple. This is your B1. It has to XOR. There's a digital XOR gate we have. Yeah, XOR gate is there. So this XOR with B2 and with B1. That will generate your G1. And then this is XOR of B1 with XOR of with B2. Sorry, with B0. B0. That will generate your G0. Let me put a probe. G2, sorry. G, oh, I see. G2, G1, G0. I think this may create an issue. Cannot directly connect B2 to G2 because of that probe connector. Let me try something else for that. Okay. Small resistor. Yeah, small 0.1 resistor. Okay, so let us simulate it. Yeah. Why is G2 showing like this? G2 should be digital. Yeah, this is the case. So I think it's because it's not in sequence, it is probably difficult for you to understand. But let us focus on 0 to 2. Okay, 0 to 2. 0 to 2, how it is. This is it. 0 to 2. What is B0, B1, B2? All are 0, 0. Okay, if you observe, all are 0, 0. And what is G0, G1, G2? All are 0, 0. Okay, they're working fine. They're working fine. That is the binary to gray code. Here, all bits remain the same. Next, what happens? B0 changes by 1 bit. Right? All the other bits remain same. So G0 also changes by 1 bit. So till here, it is all fine. Next, from 2 to 6. Let us see from 2 to 6. What happens here? B0 is 0, B1 is 1, and B2 is 0. So B0 has changed from 1 to 0, and B1 has changed from 1 to 0. So 2 bits have changed. But what happens for the gray code? G2 remains at 0. G1 changes from 0 to 1, but G0 remains at 1. So that is, there's only a change of 1 bit. Okay, there's only a change of 1 bit in the gray code. Now, here in the binary, B0 changes from 0 to 1. B1 remains as it is, B2 remains as it is. So here also what happens? G0 is changing. G0 is changing. Okay. Now, B0 goes from 1 to 0. So B0 goes from 1 to 0. B1 also goes from 1 to 0. But B2 goes from 0 to 1. So that means there are 3 bits are changing at a time. When you're in the binary, when it is going from 3 to 4. But for your gray code, G0 remains as it is. G1 remains as it is. Only your G2 is changing. Okay, only your G2 is changing. Okay, so this is like the power of your binary to gray code. Okay, how even though your binary is changing so much, your gray code only changes very slowly, very less. Okay, so that is like your gray code logic. Any questions, any queries, any feedback, anything you want to ask about this simulation, you can ask me. Okay, if there are no questions, I'm done for today. So I thank you all for joining. Thank you for your doubts. Thank you for your queries. Thank you for listening very patiently to me. I'd be happy if you could be a little bit more interactive, ask more questions, ask more doubts, and give more feedback, verbal as well as through your messages. Okay, so all the best. Kindly complete and submit your assignment 5 by Wednesday. And for those of you who have registered for the exams, kindly keep preparing. And all the best for your various other subjects which you're handling. Okay, so thank you. So I'll end this session. Okay, thank you.